last lecture we saw several examples of linear transformations. We shall now continue to study the structure of linear transformations. The answers to many of the questions that we raised lies in the study of the structure of a linear transformation. Let us now consider a vector space V and a vector space W. Both are vector spaces over a field F, and recall that a transformation from V to W is called a linear transformation if it preserves the basic algebraic operations in the vector spaces. If it preserves addition, T of x plus y is T of x plus T of y for every x y in V, and it preserves scalar multiplication. T of alpha x is alpha T of x for every alpha in F and for every x in V. Such a linear transformation is going to hold the key for our studies on various questions that we raised. An important property that we observed, a very simple but important property. So, let us note that a simple property of a linear transformation, which we saw last time, was that if we take theta v, the 0 vector in the V space, T always maps it to the 0 vector in the W space. So, a linear transformation always maps the 0 vector theta v in V to the 0 vector theta w in W. Okay. So, what does that mean? We have the vector space V and the vector space W, and T is the transformation that is taking V vectors into W vectors. What the above property says is theta V is a vector in V and theta W is a vector in W. Theta V is the 0 vector in V, theta W is the 0 vector in W. T pulls along this 0 and then maps him to that 0. This is a typical property of linear transformations. Now, it may so happen that some other vector in V may also get pulled to the 0 vector. There may be another vector which get pulled to the 0 vector. In other words, there may be a lot of vectors in V which are all going to get focused towards theta w. So, all of them are going to be focused towards theta w by this lens T. So, we collect all these vectors which are going to be focused to theta w. So, there may be several vectors in V that get mapped to the 0 vector in W, in addition to the theta v which we already know gets mapped to the theta w. We collect all this, we collect all these vectors in V which get mapped to the 0 vector, which get mapped to the 0 vector under the map T. So, we denote this collection by NT. So, NT is the collection of all the vectors in V such that they get mapped to the 0 vector. Now, clearly the first thing we observe is that NT is a collection of vectors from V having certain specific property. Therefore, a priori they are all vectors in V. Therefore, NT is a subset of V. And the second trivial thing that we know is that the 0 vector of V is certainly in NT, because the 0 vector get maps to the 0 vector. 2 theta V belongs to NT since T of theta V equal to theta W, and therefore, NT is a non-empty subset of V, because there is at least one vector, namely theta V, which belongs to NT. Now, whenever we have a non-empty subset of a vector space, the natural question that we ask is whether that is a subspace. So, is NT a subspace of V? This always, whenever there is a non-empty subspace of a subset of a vector space, we are always interested in knowing whether it is a subspace. In order to make sure that NT is a subspace, we must make sure that NT is closed with respect to the two basic operations of the vector space. So, for this to happen, NT must be closed with respect to addition and scalar multiplication. That is the major requirement for any subset to get qualified as a subspace. So, let us verify whether NT is closed under these two operations. So, let us first check with addition. Suppose we have two vectors in NT, we want to know whether their sum will also be in NT. Now, all we know at present is that x y are in NT, but NT the collection of all those vectors which are mapped to the 0 vector, and therefore, T x must be 0 vector, that means x must be mapped to the 0 vector, and T y must be the 0 vector, because x and y are in NT and therefore, they are mapped to the 0 vector. That says, I can add the two and I will get equal to theta w plus theta w, the 0 vector plus the 0 vector is the 0 vector itself. Now, we know that T is a linear transformation, therefore, T preserves addition, and hence T of x plus y is the same as T of x plus y. T x plus T y is the same as T of x plus y. That says, this is because T is linear. T is a linear transformation, we know T preserves addition. That says, the vector x plus y is also getting mapped to the 0 vector, and hence x plus y also belongs to NT. So, thus x and y belong to NT mean x plus y belong to NT, hence NT. So, the whole thing implies NT is closed with respect to addition. The next thing we have to verify is whether NT is closed with respect to scalar multiplication. So, let us take a vector x in NT. What does that mean? We want to verify that it is closed with respect to scalar multiplication. That means, when we multiply x by any scalar, the resulting vector must also be in NT. Now, first of all, we are given x is in NT, this means T carries x to the 0 vector, that is the qualification for being in NT. And if that is so, for any scalar, if I multiply both sides by alpha, I get alpha theta w, which is theta w. When the 0 vector is multiplied by any scalar, we get the 0 vector. Now, since T is linear, T of alpha x is the same as alpha of T x, because T preserves scalar multiplication. So, alpha T x is the same as T of alpha x, since T is a linear transformation. So, that says the vector alpha x is going to carry over to the 0 vector, and hence alpha x qualifies to be in NT. So, this says NT is closed under scalar multiplication. Therefore, NT, so what are the various properties we observed? NT is, so hence NT is first of all a non-empty subset of V which is closed under addition and scalar multiplication, and that makes it a subspace. So, NT is a subspace of V. This subspace is called the null space of T. This subspace is called the null space, the vectors which get nullified, null space of T. So, we have NT is called null space of T is the set of all vectors in V such that T x equal to theta w, and this is a subspace of V. Shall make one simple observation. Suppose V is a finite dimensional vector space and T maps V to W, and W is a vector space. We do not know whether it is finite or infinite dimensional space. So, it is some vector space, and that is a linear transformation. T mapping V to W is a linear transformation. Now, NT is a subspace of V, and V is a finite dimensional space. So, we observed that any subspace of a finite dimensional vector space must be finite dimensional, and its dimension should be less than or equal to the dimension of the full space, and hence we get NT is finite dimensional and dimension of NT is less than or equal to dimension of V, because it is a part of V. This dimension is called the nullity of T. This dimension NT is called nullity of T, and is denoted by say nu of T. So, what do we have? Nu of T is dimension of NT, where NT is the null space. So, the nullity of a linear transformation is just the dimension of the null space of T. So, now we have collected all the vectors which are focused to 0, and then we have studied them, and we find that they form a subspace, and that subspace is called the null space, and its dimension is called the nullity. Now, let us look at again the transformation. We have V, we have W, and T transforms V vectors to W. Now, we are say this is NT, that means all the vectors here are focused to W. All the vectors in this portion are going to be focused to W, the 0 vector in W. Now, if I take any vector that is not in NT, it will now get focused to elsewhere. This one may be focused somewhere. So, now therefore, we see theta w is one focal point, and there may be other focal points. That means, there will be other points in W where the image of a vector in V may come and fall. We collect all these focal points. So, we now look at the set R T, which is the collection of all these focal points. These focal points will be in W, these are points in W, we are trying to see where they come and fall. These are points in W such that somebody comes and falls there, his image comes here under T. That is, there exists an x in V such that the image of x under T is y. So, y is a focal point for x, then he is taken into R T. If y is not the focal point for anybody, he is not going to be in R T. So, R T is the collection of all such y for which there is a pre-image x such that T x equal to y. We also say that y, the R T is the collection of all the values taken by the function T. T of x is the value of the function at the point x. So, y is the value of the function T at the point x. We are collecting all the possible values that the function T takes. Now, clearly, since this is a collection of vectors in W with certain specific property, it is a subset of W. R T is a subset of W, and we have already seen that theta V goes to theta W. Therefore, theta W is one of the values taken by T. So, theta W belongs to R T since theta V belongs to V and the value of T at theta V is precisely theta W. So, there is at least one point in R T, therefore, R T is a non-empty subset of W. So, that implies R T is a non-empty subset of W. And as we looked in the case of NT, whenever we have a non-empty subset of a vector space, we are always interested in knowing whether it is a subspace. So, is R T a subspace of W? It can be a subspace of W because it is a subset of W. Once again, in order to check whether it is a subspace of W or not, there are two properties that we have to check, whether it is closed under addition and whether it is closed under scalar multiplication. So, let us check whether it is closed under addition. So, suppose I take y 1 and y 2 in R T, we want to know whether y 1 plus y 2 is also in R T. Now, first of all, what does it mean to say that y 1 is in R T? Y 1 is in R T means it is a focal point, which means there is a pre-image x 1 in V such that T of x 1 will be focused towards y 1. T of x 1 is y 1. Similarly, y 2 is in R T means there exists an x 2 in V such that T of x 2 is y 2, which implies there exists x 1 x 2 in V such that T of x 1 plus T of x 2 is y 1 plus y 2. Now, since T is linear, T of x 1 plus T of x 2 is T of x 1 plus x 2. So, this means there exists x 1 x 2 in V such that T of x 1 plus x 2 is equal to y 1 plus y 2 since T is linear. Since C is a Taylor transformation, T of x 1 plus x 2 is the same as T of x 1 plus T of x 2. Now, if we call x 1 plus x 2 as z, then since x 1 is in V, x 2 is in V, x 1 plus x 2 will also be in V because V is a vector space. So, there exists z which is equal to x 1 plus x 2 in V such that T of Z is y 1 plus y 2. This means y 1 plus y 2 is also a focal point with Z being focused at y 1 plus y 2. That is, the value of T at the vector Z is y 1 plus y 2. So, y 1 plus y 2 is a value taken by T, therefore, y 1 plus y 2 also belongs to R T. So, if y 1 and y 2 are in R T, y 1 plus y 2 is also in R T, which means R T is closed under addition. The other thing that we have to check whether R T is a subspace or not is to see whether R T is closed under scalar multiplication. So, take a vector y, let us say take a vector y in R T. We want to know whether alpha y will also be in R T. If y is in R T, that means y is the value taken by T at a point x, that means there exists an x in V such that T x equal to V, T x equal to y. If T x equal to y, if we multiply by alpha, alpha T x will be equal to alpha y for every alpha in F. Once again, since T is linear, alpha of T x will be T of alpha x. So, there exists a vector x in V such that T of alpha x is equal to alpha y. Now, if we call alpha x as Z, so since x is in V, alpha is a scalar and V is a vector space, therefore, it is closed under scalar multiplication. So, Z equal to alpha x will belong to V such that T of Z is alpha y. That means, alpha y is the value of T at the vector Z, or it is a focal point for the vector Z, and hence alpha y must also belong to R T. So, that says R T is closed under scalar multiplication. Thus, we have R T is a non-empty subset of W, which is closed under addition and scalar multiplication, which means R T is a subspace of W. So, R T is a non-empty subset of W, which is closed under addition and scalar multiplication, and hence R T is a subspace of W. This subspace is called range of T. So, the range of T, which is denoted by R T, is equal to all those y's in W such that there exists an x in V whose image under T is y, and this is a subspace of W. If W is a finite dimensional vector space, then R T being a subspace of this finite dimensional subspace W will also be finite dimensional, and since it is a subspace of W, dimension of W will be less than or dimension of RT will be less than or equal to dimension of W. This dimension is then called the rank of T. This dimension is called rank of T and is denoted by rho T. So, rho T is just the dimension of range of T by definition, and rho of T will be less than or equal to dimension of W. So, suppose now we have V finite dimensional, say dimension of V is n, and say W finite dimensional, dimension of W equal to m, and T is a linear transformation. So, I have two finite dimensional spaces and I have a linear transformation T from V to W. Now, we have seen one subspace of V which is connected with T, namely the NT, and we have seen one subspace of W which is connected with T, namely range of T, and this N of T is a finite dimensional subspace of V and its dimension is called nullity, and that is denoted by nu T. So, its dimension is nu T, and here the dimension is rho T, and this dimension is smaller than or equal to n and this dimension is smaller than or equal to n. So, nu of T is less than or equal to n and rho of T is less than or equal to m. So, we have two important subspaces associated with a linear transformation G. As we go along, we will see a lot of subspaces that are connected with a linear transformation, and these subspaces come into play in the analysis of the structure of a linear transformation. Let us look at some examples. Consider V to be Fn, where F is a field, W to be Fm, where F is a field. So, from n component vectors or the n column vector with n entries to the column vectors with m entries. Now, we have a transformation. How did we define a transformation from V to W? In the last lecture, we saw any m by n matrix will generate a transformation, a linear transformation from Fn to Fm. So, let us now consider a fixed matrix in a fixed matrix. So, consider a fixed m by n matrix with entries in F. Then we defined a linear transformation T A from Fn to Fm as T A takes any vector x to the vector A times x, and since A is m by n and x is n by 1, the result will be m by 1 and therefore, it will be in Fm. We have already seen in the last lecture that this is a linear transformation from Fn to Fm. So, we have seen that T A is a linear transformation from Fn to Fm. Now, once we have a linear transformation, we want to know what is its null space, what is its dimension, what is the range space and what is the dimension. So, let us look at the null space of T A. So, in order to find the null space of T A, we want to find all those vectors which get mapped to the 0 vectors. So, x in V belongs to the null space of T if and only if somebody gets qualified to be in NT if and only if it gets carried to the 0 vector. So, if and only if Tx is theta w, but then the definition, I should put Ta. The definition of Ta is that Ta of x is A times x. So, the image of any vector is obtained by pre-multiplying it by the matrix A. So, therefore, Ta of x is A of x equal to theta w. What is theta w? It is theta m, because w is Fm. So, this is simply the homogeneous system of equations Ax equal to theta m, and the solutions of this is what is known as the null space of the matrix A. Okay. So, if and only if x belongs to the null space of the matrix A, that is the set of all solutions of the homogeneous system Ax equal to theta. So, the null space of T is the same as the null space of A. For example, if we take m equal to 2, n equal to 3 and consider F2 to F3 to be our V and F2 to be our W, we have to look for a matrix in m by n, Fm by n. So, remember we want to, when you go from n component to m component, we need a matrix which is m by n. In this case, we have m is 2 and n is 3. So, we have to take a matrix which is 2 by 3. So, let us say 1 0 minus 1 0 1 minus 1. Then the transformation T A is T A of x. Now, x is in F3 will be A times x. Since x is in F3, A is in 2 by 3, the result will be in 2 by 1 and therefore, it will be in F2. Now, what is the null space of T A? It must be equal to the null space of A. Now, what is the null space of A? The set of all x in Fm such that Ax equal to theta m. Now, what is Ax? A is this matrix. I do not know what x is. X must be in F3. So, it must have 3 components, which means 1 0 minus 1 0 1 minus 1 into x1 x2 x3 is equal to theta 2. Now, the matrix A is already in row reduced echelon form, and therefore, we can write down the solution by inspection by eliminating 2 of the pivotal variables. There are 2 pivotal variables x1 and x2, and the non-pivotal variable is x3, and we can eliminate x1 and x2 in terms of x3. We get x1 equal to x3, x2 equal to x3, and therefore, the null space of A consists of all vectors for which x3 can be chosen arbitrarily, the non-pivotal variable. Once you choose the non-pivotal variable, the pivotal variables have to be chosen to be equal to that, and alpha can be chosen arbitrarily. And we have therefore, NT also equal to this, because NT is equal to NA. Now, what is the dimension of NT? Since the vector 1 1 1 is a basis for NT now, NT is the same as NA, I should write NTA, and since the basis has exactly one vector and the number of vectors in a basis called dimension, we get dimension of NT is 1, and this dimension is called nullity. Therefore, the nullity of T A, which is nu T, is 1. Now, let us find the range of T A for this same transformation. First, let us look at the general matrix and then look at this example. So, once again we look at Fn to be V, W to be Fm, and we take a fixed matrix in Mn and we look at the linear transformation which takes the vector x to A of x. Now, we want to find the range of T A. What does this range of T A mean? We want to know the vectors which are all focused by the vectors in x. So, we want to look at the range of T A, the set of all y in Fm, that is the W, such that there exists an x in V, V in this case is Fn, such that T A x is equal to y. This means we are looking at there exists an x in Fn such that, but now again T A of x is multiplying the vector x by the matrix. But this means we are looking at all those y for which the non-homogeneous system has a solution. So, this is the set of all y in Fm such that the non-homogeneous system A x equal to y has a solution, and this is what we call as the range of the matrix A. And the dimension of this is called the rank of A. So, the dimension of RTA is the same as dimension of range A, is called the rank of A, and it is also because the dimension of the range of TA, it is the rank of T. Then let us go back to that example 1 0 minus 1 0 1 minus 1 mapping F, then we have T A mapping F 3 to F 2 where T A of x is A x. We have already found the null space of this matrix, we shall now find the range of this matrix. So, now we want to know for what y's A x equal to y has a solution. So, look at the non-homogeneous system A x equal to y. That means, A x is x 1 minus x 3, x 2 minus x 3, that is what A x is. If you take a vector x 1, x 2, x 3 and pre-multiplied by the matrix A, you get this, and we want this to be equal to y 1 and y 2. We want to know for what y 1 and y 2 will this system have a solution. We see that whatever y 1, y 2 we choose in F, the system has a solution x 1 equal to y 1, x 2 equal to y 2, x 3 equal to 0, because A into x 1, x 2, 0, I am sorry, y 1, y 2, 0 is precisely equal to y 1, y 2, and therefore, given any y 1 by 2, we are able to construct a solution. Therefore, every y in F 2 belongs to R t, and therefore, R t is all of F 2, and hence or T A or T A. Therefore, rank of T A, which is rho T A, is 2. So, thus we have a very simple example of a linear transformation from F 2 to F 3 to F 2, for which we have found the null space and the range. Let us now look at another example. Let us consider V to be the collection of all polynomials of degree less than or equal to 4 with coefficients from F. we will now look at a linear operator, that is a linear transformation from V to V defined as d of any p is dp by dx, the differentiation operator. We had seen in the last lecture that this is a linear transformation or a linear operator. We have seen d is a linear operator on f4x. Our V now is f4x. So, let us find the null space and the range of this operator. So, let us find null space of D. So, we want to find those vectors in V which get mapped to the 0 vector under the transformation D. Now, vectors are all polynomials because our vector space is the space of all polynomials. So, we want to find all those polynomials which when differentiated gives me the 0 polynomial. Go to 0 vector, 0 vector is the 0 polynomial. So, x belongs to the null space of D if and only if dx is the 0 polynomial, that is if and only if let us use the notation p because we have polynomials. So, dp equal to 0. Now, dp by definition is dp by dx, that must be equal to 0. That is how the transformation D is defined. The transformation D is the differentiation transformation. So, dp by dx equal to 0, the derivative is 0 if and only if p is a constant. So, therefore, only the constant polynomials qualify to be in the null space of D. So, thus we get the null space of D is the set of all polynomials in the vector space which are of the form p equal to some constant a naught belongs to f. So, they are all constant polynomials. Now, what is a basis for this space? Well, the constant polynomial 1 is a basis for this space. So, p equal to 1 is a basis for n d because everybody else is a multiple linear combination. A naught times p will get all the vectors in n d, and therefore, dimension of n d is equal to 1 because we have a basis consisting of one vector, and since the dimension of the null space is 1, the nullity of D is 1. So, thus we have found the null space of this differentiation operator on f4x and the nullity. Now, let us look at the range of D. So, to find the range of D, we want to find all polynomials p in f4x. Remember, now we are looking at D as a linear operator on V. So, even the W space is now V. So, the W space is also V4x. So, we are looking at all those p in f4x for which we can find a pre-image. What does that mean? We can find a q which is also in that same space because a linear operator such that the image of q is equal to p. So, we want to find all those p's which can be obtained as the image of a q in f4, which means we want dq dx must be equal to p. So, we would like to find those p's for which dq dx will be equal to p. Then q must be equal to integral 0 to x p x dx. But then if you take any polynomial of degree 4 the integral will become a polynomial of degree phi. And therefore, in order that q belongs to, we want q to belong to f for x. So, in order that q is a polynomial of degree less than or equal to 4, p must be a polynomial of degree less than or equal to 3. So, only polynomials of degree less than or equal to 3 have a pre-image. So, in order that q belongs to f for x, it is necessary that p belongs to f 3x, it is a polynomial of degree less than or equal to 3. Hence, the range of D is the set of all polynomials in f for x such that p belongs to only the f 3x. They are of the form p is equal to a naught plus a 1 x plus a 2 x squared plus a 3 x cube, where all the aj's are in f. So, R D consists of all polynomials of degree less than or equal to 3. Now, what is the dimension of R D? We have seen that 1 x, x squared, x cube form a basis, and therefore, the dimension is 4, and therefore, rank D, which is rho D, is equal to 4. We will see one more example similar to the one above. Take V equal to f 4 x and then say W equal to f 3 x, and then consider the transformation D, let us call it as T, because D we use for differentiation, T mapping V to W defined as T of P is the second derivative of P. Now, again in the last lecture we verified that this is a linear transformation from V to W. So, T is a linear transformation from V to W. The once we have the linear transformation, we want to find its null space and the range. So, let us find the null space of T. Now, the null space of T is all those vectors which get focused to the 0 vector, and vectors here are all polynomials. So, P belongs to the null space of T if and only if it gets focused to the 0 polynomial, or its value under T is the 0 polynomial. If and only if T is defined as d squared. So, it is d squared P by dx squared is 0. This means P x is a linear polynomial a naught plus a 1 x, where a naught and a 1 belong to f. Therefore, only linear polynomials qualify to be in the null space of T. So, therefore, we get null space of T consists of all those polynomials in f for x which are of the form P x equal to a naught plus a 1 x, a naught a 1 in f. Now, clearly P 1 equal to 1, P 2 equal to x is a basis for n t, because as is seen here every other polynomial is a linear combination of the polynomial 1 and the polynomial x, and therefore, they form a spanning set and they are obviously linearly independent, and therefore, they form a basis. So, the dimension of n t, since a basis consists of 2 vectors now, the dimension of n t is t 2. So, the nullity is this dimension is 2, which implies the nullity of t, which is defined to be the dimension of n t, is 2. Let us now look at the range. The range of T, we want to find all polynomials P in now the W space is F3x, our W space in this case is F3x. So, we want to find all those polynomials in F3x, that means polynomials of degree less than or equal to 3. We want to find all those polynomials for which there is a pre-image, for which there exists a Q, pre-image must be from V is F4x in our case. Therefore, Q belonging to F4x such that TQ equal to P. If we want TQ to be equal to P, since T is defined as d squared Q by dx squared, we want to find those P's in F3x for which we can find a Q in F4x, so that d squared Q is equal to dx squared. Now, if Q has to be in F4x, if Q has to be in F4x, it is a polynomial of degree less than or equal to 4, and so when we differentiate it twice, it will lose 2 degrees. Every derivative reduces the power by 1 in the polynomial, degree by 1 in the polynomial. So, if we take any polynomial in F4x and differentiate it twice, on the left hand side we will get only polynomials of degree 2 or less, and therefore, P has to be a polynomial of degree 2 or less. Okay. Since Q belongs to F4x, we have d squared Q dx squared belongs to F2x. It has to be a polynomial of degree less than or equal to 2, and hence P has to be in F2x. So, we know that if at all there is going to be a solution for this, we better start with P which is in F2x, but then for every P in F2x, if we define P Q to be integral 0 to x P x dx, then since P is a polynomial of degree less than or equal to 2, when I integrate it will be a polynomial of degree less than or equal to 3, and if I integrate further I will get a polynomial of degree less than or equal to 4. So, Q will be in F4x, and if we differentiate, that is d of Q will be precisely P, and hence P will belong to range of D. Therefore, range of D is precisely F2x. What we have shown is, you take any vector in F2x, it is in the range, and previously we showed that if it has to be in the range, it has to be in F2x, and therefore, F2x is precisely the range of FD. So, the range of D is F2x, and therefore, the dimension of RD is dimension of F2, which is 3, because 1 x squared form a basis for all polynomials whose degree is less than or equal to 3, less than or equal to 2, and therefore, the rank of D is 3. So, these are some simple examples of looking at the range and the null space. Now, what we have so far is, here is the vector space V, here is the vector space W, and the dimension of V is equal to n, say, dimension of W equal to m, say, and there is a linear transformation T, and then a part of this is what is known as the null space of T, and a part of this is what is known as the range of T, and the dimension of n of T is what is known as nu of T, and the dimension of rho of R of T is what is known as rho of T, and since null space of T is a part of V, we have nu T is less than or equal to n. Similarly, we have rho T is less than or equal to n. Now, we have one subspace on V which comes from T, we have one subspace on W which comes from T. Is there a connection between these two? And there is a connection between their dimensions, and that is what is known as the rank nullity theorem. We shall first state this and we will look up proof of this in the next lecture. Now, what is the statement? Let us look at the three examples we had. In each of these examples, if you see the first example, so let us see and take the last example. We have that n is 5 in this case, because F4 m is 3. So, n is 5, nullity was 2 and rank was 3, and the rank plus nullity came out to be, in this example we got rank D plus nullity D was equal to 2 plus 3, which is 5, which is equal to the dimension of V. And now, this is not an accident, and the fact that this is not an accident and this is always true for linear transformations is known as the rank nullity theorem, which we will look at in the next class.